I think I'm getting an echo. Is it fine now? Yeah. Okay. So welcome to the second session of day 3 under the project Education for Technological Literacy and Inclusion. And now we are going to look at a couple of other cases. In the last session, we were talking about the classification problem. And now we'll move on to regression and then later on to clustering. Okay. So I hope I'm audible clearly. Okay, great. So let me just quickly share my screen. All right. Okay. Don't worry, in these two cases, we are going to use very simple data sets. I think I made a mistake of taking a huge data set for the classification problem. But I think it also helps us to, whatever cleaning or pre-processing that we have done, similar things can be done for any kind of data set that you get for any kind of machine learning problem. But here now we will see something with more straightforward data sets with very few rows, right? So just to give a brief introduction about the regression problem, and I'm sure all the economists in this class know it much better than I would. So it's just a method to model the relationship between the dependent or the target variable and our independent variables. Can be one or more independent variables. Accordingly, we can call it a simple regression or a multiple regression. Right? And as Bakshish also must have pointed out yesterday, it's a supervised machine learning technique. Because the data is labeled, we know what we want to predict. The only difference from classification problem is that we are going to predict a continuous value and not a discrete one, right? So yeah, and we want to find the best fit line or curve in the data that will help us to predict the values. And some use cases, anything that is continuous variables, right? So price estimates or weather forecasting, even time series forecasting, you can consider it a regression. It's just that the data we use is specific. It's like historical data, you could say, and maybe sometimes you use external factors also. But yeah, these are some of the common use cases we can say. And now we are going to do sales prediction using linear regression. So I'm just using some sample data which is available in Kaggle, and Bakshish has already shown you where you can find all the data sets, and I've just put the link here in case if you would like to download it. So let me go straight to the notebook. Okay. All right. Are you able to view the notebook, the Python notebook?
Yes, we can see it. Thank you.
Thanks. So here again, I'm just going to use a data set which is having some features about the money spent in different kinds of advertising media. So television, radio, newspaper, and how is our sales doing based on that, right? We are just going to go through the normal process. Again, we have to import our libraries, pandas and numpy for all kinds of analysis. These are for visualization, and this is just to ignore some warnings that we may get due to versioning updates, etc. And I am reading my data, okay, and I am just having a look at it. So there's not much of exploratory data analysis to do in this particular case because it's also a very small data set, has only 200 rows and 4 columns, right? And you can use a .info method just for you to see, okay, what are the types. All of them are float or numerical, non-null, right? So all of them are numerical, so you can use the describe method to get these values, your mean, your standard deviation, and your min max, etc. Okay, and like we already saw, no null values, so no treatment as such required. Here we are just going to, we are using a functionality from Seaborn, a library called pair plot. So you have your you have your dependent variable, that is sales in this case, on your y-axis, and you are just observing, the different scatter plots based on the different x variables or the explanatory variables, right? And as it is, it's looking quite clear that television advertising has, there's a clear trend. You can see that the more you advertise in television, the more the sales, so to say. And for newspaper and radio, it looks rather more randomly scattered, right? Now, this is all like a little bit of a repetition because we are just, using the same methods, right? The only difference will be in the model that we use, because the analysis, all the commands, the functions that use are going to be more or less the same. So we're again using the .core method, and we can use the heat map to get the correlation matrix here. And like we already observed visually, the correlation is very high between television and sales, and whereas it's very low for newspaper or even for radio, right? So yeah, then I'm just following the steps as the normal process. Okay, outlier analysis. We can do box plots and not, okay, seems like there are a couple of outliers in the values of newspaper. But in this particular case, we are just going to use one of the variables. We are not going to do multiple regression. We'll do a simple linear regression. So I'm only going to use my variable TV, right? So which has the, as you can see, the most impact or the highest correlation with our target variable or the dependent variable, right? So we're going to perform a simple linear regression, and so we'll have just this equation, right? And go straight to the model building. So since we have only one variable, one independent variable, which is TV, so I'm calling that X. This advertising is the name of the data frame that I'm using, right? If you remember, I had read the data into advertising, right? I read this file and I have stored it under advertising. That's the name of my data frame. Okay. So here, yeah, I have defined my X and I have defined my Y as the sales, which is what we want to predict, right? And again, we use the same libraries to get the remaining features. Train test split is what we need to do next. So my X and Y will be split into a train set and test set based on the size that I give. So in this case, I'm using 70% of the data as train data and 30% as test data. And I don't know if you noticed before, so you can see that the train test split is going to give you 4 different data frames. That's the output that is defined for this function, right? So it's automatically going to generate X train, X test, and Y train and Y test. So we will first train using X train. We will fit X train against Y train, and then using that we can predict, based on X test, what are the values we get, right? And then we will compare with Y test to see the accuracy of our prediction, so to say. Okay. So here I'm using this library stats models, and I'm calling it as SM. And I am adding a constant here to my X train. So it's an inbuilt feature under this stats models module. So I'm adding the constant here to X train, and that I'm going to assign a new name for it, or I'm storing it into X train underscore SM. And here I am already, training the model. I'm fitting the X train against the Y train, right? ordinary least square method. And yeah, it's quite straightforward, I guess. And here you can you have this attribute for the model. So LR is for linear regression, just an abbreviation. And if you can name it whatever you want. Okay, it's just for convenience. And you have the dot params attribute, which will give you the values, so you can get the constant, the intercept, and the slope of the regression line. And here, if I go further, I can print the summary. So this is my model based on the train. I can print the summary of the regression, the results, right? Now, here I guess you will see many terms which were discussed in the June seminar. So I suppose these values would be already familiar to you. I'm not so good at interpreting this, but yeah, Beatrice, if you'd like to add anything, please feel free. The only thing I can comment is, yeah, your p-value is much smaller than 0.05. So this e raised to minus 52 is just telling us it's a super small value. So yeah, and as we already saw from the scatter plot itself, we can see that this variable has a significant impact on the sales, and they are highly correlated. So yeah, based on these results, we can also, you get to see, the t statistic and AIC, BIC, F statistic, R squared, everything in a single table. Now you will have other attributes also, which you can check in the documentation. Apart from summary, there'll be other things that can be printed as well, like in a confined format. So based on my intercept value, based on the constant, I am just here saying that, okay, this is the equation that I'm getting for my simple linear regression. And I am just trying to put that visually here. So for the training data, right? So for the training data, which is 70% of the total data that we had, this is my plot. So it's just you are plotting a line also based on the equation, and you can this just giving the color, and so it's like two plots together, right? So you can do a scatter plot, and then you're plotting the line as well, and then you get this kind of a diagram. So you see that, okay, it is making sense, right? It's a significant, I mean, it's a good fit, you can say. So, but we will also evaluate the model. This was just the training, right? And now for model evaluation, we are going to predict our uh, values. So, wait, sorry, I'm just checking here. I have mentioned white train. Ideally, this should be white test. Okay, it's just we are going to predict on the test data. That's how we do. But also, even for the train data, we can check the residuals, and I think that's what I wanted to do here first. So we're calculating the residuals. So based on my prediction, so basically the difference between these points and the line, no, those values are my residuals. So the white train minus the white train predicted from the model, those are my residuals, and I can do a distribution plot of the residuals to see, okay, am I getting a normal distribution, and we are getting a normal distribution. So ideally we are good to go. Now we go to the test set, right? So again, I will do the same steps for the test set. I am adding a constant and getting my X test, which I'm going to use in the model. Here, linear regression, LR. and I'm calling that model to predict my values. So for the test data, what are going to be my predicted sales information, right? My Y variable, the explained target variable. So now we'll see we can calculate the remaining evaluation metrics. So you can use the sklearn library. You have different kinds. You will have more options than this also. Here I just considered the squared error and R square value. So you can calculate the root mean squared error. Just you can, so we are doing it kind of manually. We are taking the square root. So that's why it's always a combination of functions, you can say. So we are calling numpy and we are doing the square root of the mean squared error. And mean squared error is already defined for us. Python already knows how to calculate that, right? So we give our input as y-test and y-pred, and we this is the value we get, right? Similarly, R square. So this is already an inbuilt function. You just have to call it and give your input y test and y prediction. So the original test data set sales values and the predicted sales values, right, after running the model, and you get your R squared value. And then we can do the same exercise that we did earlier to plot the scatter plot against the regression line. And yeah, you can like observe the goodness of fit, so to say. So I think that was a very short case study for regression. But is it
Excuse
clear?
me, Merlin.
Yes.
Can we recap? Maybe I can recap. As far as I understood, we took 70% of the data.
Yes, we took 70%.
And we performed the regression for 70% of the data. Okay. Well,
yes.
Before we tested for homoscedasticity, that is, we tested for outliers, and we saw that it was homoscedastic. And even before we saw one by one all the explanatory variables on the dependent variable.
Yes.
Once you tested the model for 70% of the data, and then you take the remaining 30% of the data and perform the regression analysis to see whether it works properly. Is this correct?
Yes, that's exactly right.
Yes.
So,
and then can we go to the results, to the testing of the 30% data, please?
The testing. So yeah, you get the R square and the.
So how do we get to know that it is working properly? The R square, maybe the R square, because the R square is 0.79. So
yeah,
this is a very high R square.
Right.
So the fitness is perfect, is correct.
Right.
And even the scatter plot, you can see in the scatter plot the fitness.
Yes. So that's.
So am I right?
Yes, absolutely. Yeah, mainly we just see the R square value and it's it's looking good, like it's at a higher end. So that's how we can say that okay, this is a good fit for our regression. But here, like it was quite clear, like it's a very straightforward example since we saw that even by observation there's a clear line that you can fit here, right? So I just took a very straightforward example because I mean, and here the code is also easy. You're not doing so much of what do you say, pre-processing of the data. And what I will also show you is that you can, like, I mean, for your own practice or exploration, I know Bakshish showed you in Kaggle what all can be achieved in terms of finding data sets. But I just wanted to show that, okay, for example, this is the data set that I used, right? And I provided the link on the slide. You can also go here, there's an option called code, and you can see various notebooks. So the works of different people, how they have done their own analysis, right? So I mean, this one, it's just a small data set, and maybe everybody has similar analysis. But if you take a larger data set or something specific to your field, you can also go to code and you can see all the different notebooks that different people have worked on. So it gives ideas about like what kind of inferencing you can do from that specific data. Right? So just as a resource, I'm just letting you know.
Yes. Lovely. I have a question. And what will happen if we see that the model doesn't work? I mean, with the remaining 30% data, maybe we should do a transformation. Maybe you set up a linear model, but maybe it is an logarithm. So maybe we should transfer through logarithms, or no?
Yes, yes, yeah. Sometimes, yeah, the values. In fact, even for the classification model that I was explaining, uh, there is a thing called feature scaling, right? So in the classification model, if you remember, we had a feature called monthly expense, which was in various numeric values, and then we also had a feature about something categorical, which was in terms of 1010. Now, when it goes to the model, maybe it is not the best way to put it, right? You have such varied numbers, and it's important actually to bring them to one particular scale. So you have different scaling options. You have min-max scaling, or there is one more, I forgot the name, a standard scaler. So that kind of helps to bring the whole data, like, yeah, transforms it into a particular scale, and that data then you use for your modeling. And once you finished the modeling and the predictions, then you scale it back to the original. But I did not do that for the classification problem, because
Yeah.
finally the best fit that we found was mostly the random forest classifier and the XGBoost. So for the tree-based methods, we do not need to scale the features. But yes, for otherwise, it's actually important to scale. Yes, thank you, Beatrice.
Thank you, Merlin. Any more questions?
Okay. So,
Okay, Merlin, you have the floor.
okay, thank you. So then I thought we can go on and look at the cluster analysis as well. That's also a relatively small data set. It wouldn't take much time. So we will also stay on schedule. So I will just go ahead with that. Let's see here. Okay. So cluster analysis, basically, it's a machine learning technique which is unsupervised. So we do not have a labeled, let's say, target variable, right? We just have data points, and we want the machine to kind of categorize or make clusters based on some similarities, right? So the idea is to have groups of data points with some similarities, and then there are other groups which have other kind of similarities between them, right? That's a very vague explanation, but this is what we mean by unsupervised, that there is no label on what we want to get, you know. So different use cases, the most common one you can think is market segmentation, customer segmentation. Based on somebody's buying patterns, you can group them as, what kind of customer that person is, right? Even image segmentation I put because like sometimes even in our what do you say, in our Google Photos, like I think Bakshish was explaining this yesterday, that they recognize, right? So similar images may be, clustered together into one category, one cluster, but the machine may not necessarily know. For example, if it's cats and dogs, it may just, based on some features of the image, it may just, cluster it into one category without actually knowing that, okay, this is a cluster of dogs and this is a cluster of images of cats, etc. So these are just some idea for use cases.
Excuse
And
me,
we,
Merlin.
yeah,
Maybe we could also cluster words.
Yes,
You
yes,
say image, it could be clustering words, so as we can do sentiment analysis.
yes,
That
yes.
is the analyzing the text, clustering words, for instance. And this
Right,
is
right,
connected with your image segmentation. Thank
right.
you.
Yeah, sentiment analysis is also possible. So thank you. Right. So for this case, I've chosen a common problem, which is customer segmentation. Again, we are going to use a very simple data set. Let me go straight to the code. All right. So again, we are importing our UIs, and I am reading my data. I have already downloaded the data and everything, so I'm not really showing how to get to this point. But if you'd like to know, I'll be happy to help you one-on-one later, like how to navigate in the notebook. So we are reading our data here, and okay, you can see I have customer ID, I have gender, age, annual income, and a spending score, which is already calculated and kept. So it's a simple data set, again, only 200 values, except gender, everything else is of a numeric value. And we are seeing the same things, the correlation matrix, and yeah, I don't think there is much to discuss. Somehow you can see there's a negative correlation between spending score and age. So yeah, that's just something to observe. And we are just doing a count plot here for all of the variables, uh, in general. Okay, how does our data look like basically, right? What is the data that I have? It's just to observe. And what are the age groups, like how many people, of different age groups are there in my data set. So you can see more or less all ages. And the spending score and annual income plotted here in a bar plot. So this is just for observation. You can use all Seaborn library is quite good. I mean, you get more good looking uh, visualizations. But I will just say that also sometimes the Python images are not like of that high quality. Like just giving it as a tip that we were always encouraged to use visualizations from Excel or other visualization tools, maybe from Power BI or Tableau, instead of using like copying this as an image. And when you put it in a PowerPoint, it doesn't look as good, is the feedback that I have always received. So what you can do is from your notebook, from your Python analysis, you can do all the pre-processing for the data and get it into the desired format. And that data you can just simply use for a visualization in Excel. And I think Bakshish had also explained how to do some visualization in Excel. So you can use Python to get the data out into the desired format, right? So now first here I'm going to consider, so mol data is basically the data set. I'm calling it mol data. I am considering the second, third, and fourth columns. So this is just a way of fixing which all indexes I want. So I'm just kind of taking one part of the data here, right? So if I say 2, 3, and 4, basically I'm using these three columns, right? I'm using age, annual income, and spending score for my further analysis, right? So I'm calling that X, okay? Now, here I am going to use something known as k-means. So for cluster analysis, it's going to it's going to rotate across some points and kind of fix on certain centroids, so to say. And then the points which are closest to that will kind of be considered as part of that cluster. Um, it can be explained better, but please feel free to correct me if there's something that is not making sense, right? So, but vaguely, this is what you see. Okay, K means clustering. You can use this concept. that the points closer to the centroids, to each centroid, you're considering those as separate clusters, right? So here I'm calculating something known as WCSS, which is within the cluster. I forgot the full name, full form, sorry. But as you can see here, I am looping over a range from 1 to 11. So I'm just trying to see how many clusters should I ask Python to make for me using this method. So I'm going from 1 to 11, just, okay, one cluster doesn't make any sense actually, but yeah, 2 and more, right? What is the optimal number of clusters that we want? You know, so it's going to iterate over these values and it's going to do the fit for all of them, right? And then we get these values for WCSS. And now to see which is the best number of clusters, the
Excuse
most
me,
optimal.
Merlin. Excuse
Yeah.
me, Merlin. Es que we can hear a telephone, the WhatsApp of a telephone. Can you mute it, please, someone? Thank you.
Thanks. So here we have calculated WCSS for, from range from 1 cluster to 11 clusters, and we are going to use something known as the elbow graph to see, okay, what is our optimal number of clusters. And what we want to see is that where does it start declining? So from that point, that should be like our optimal number of clusters. That's how we kind of determine how many clusters we want in our analysis. So here, okay, visually we're going to kind of fix on 5, because here you see that after this point, we see the WCSS values are declining. So I'm going to give the number of clusters as 5, right? And these are.
Excuse me, I think you have minimized your screen.
Oh, okay, sorry. Let me share again. Are you able to see?
Yeah, now it's correct.
Okay.
Yeah, thank you.
Thank you. Okay. So here I have, I am giving the input as 5 clusters, and it will predict for me, okay, which data points will belong to which clusters. So as you can see, there is no, we are not going to compare. There's no label, right? We don't have a specific target variable or an explained variable, right? We just have our values, and we are just going to see, okay, which cluster does each value belong to. And based on the results, we can create scatter plots of all the clusters, and it can. So in this case, because we are using 3 different values for our analysis, it's going to be a 3-dimensional plot, although it doesn't exactly look like that. But you can see here the 3 dimensions, and more or less you can see, okay, similar colors are falling into the, each cluster is of a different color. But for easier visualization, I've just, done the same things. If you use only 2 of the variables, so if you use only your annual income and your spending score, then also you build the model in the same way. You use your elbow method, you determine 5 clusters, and again you can plot in a 2-dimensional format. So here you see that, okay, these are my 5 clusters more or less, and these yellow dots are going to represent your centroids, right? Which are the central points in your k-means clustering method. That's what I wanted to share for cluster analysis using k-means. There is also, there are other ways also that you can do. I'll just show you another notebook just briefly. Sorry. Okay. Okay, So this is just another way of segmenting. This is specific to customer segmentation. It is, yeah, it's not exactly machine learning, but I just thought it might be interesting to know in terms of customer segmentation, you can use your data about the buying patterns of the customers to determine some variables like recency, frequency, and monetary elements, right? So recency is going to tell me which other customers, what is the, how many days ago did they visit the store? Frequency is going to tell me the number of times that the customer visits, and monetary is their spending, right? So based on the RFM score, we can also segment customers into different categories. So this is just another approach of looking at it. It's, you can even manually define your customers. Like you can manually say, okay, if the customer has a high score in monetary and a high score in frequency and a low score in recency, means the person has visited our store very recently, then those are very loyal customers, or like that's basically the idea. So this is just to show you the different segments, right? For each case, you can, so here also you can say it's like 5 clusters more or less, but based on your RFM. And it's very obvious that the best class or the most loyal customers, they have a high monetary, high frequency values, and low recency. And the hibernating customers, they have not come for a long time, so the recency is very high, means it's been many days, and the frequency is on the low side, and also the monetary, the spending is also on the low side. So this is just another option of customer segmentation, another method to do it, right? Apart from that, you also have, in terms of unsupervised learning, we also have something called as association rules, or that can take you to a market basket analysis, wherein you just see the relationship between, again, the buying pattern. I think Bakshish gave the example of some kind of relationship between men who like whoever buys diapers also buys beer. So but like similarly, you can also see, okay, in a store, based on the data that you get, if someone is buying milk and bread, maybe they are bound to buy butter also along with that. So that's just market basket analysis, which is also you can create association rules like based on the data that you have, which is also actually unsupervised learning. There is an algorithm called a priori algorithm, which can be used to create these association rules. And based on that, maybe you can implement different things. The stores will also arrange their products in such a way that they are somehow related, that it's easier for the customers to navigate. I'm just giving some practical idea to what we've been doing, right? So yeah, actually for cluster analysis, that's pretty much what I wanted to talk about. I know these 2 case studies have been super short because we didn't really do any data pre-processing or anything of that sort. But if you have any doubts or anything, even in terms of code, if you want, we can look at that, if there is anything.
Excuse me, Merlin.
Yeah.
Thank you so much for your lovely presentation. Can I request we go to the last cluster, not this one, the previous one, the scatter plot, please. Can we go to the scatter plot?
Sure.
Yes. So maybe we can analyze a little bit this, okay? So we have 2 variables here. We are analyzing the topology, okay? So how the different points are clustering together. So how many, I would say we have 1 here, the blue ones is 1 cluster, the purple one. So this means the blue one is 1 cluster. This means that these are families with low annual income, and low spending. Is it correct?
Yes, right.
Then we have a second cluster up there, the purple one, the purple up there, and they are very nicely, the points are very nicely together. These would be families with low annual income but high spending score. Is it correct?
Yes, absolutely.
Then we have a third group of people. Third group, the red one would be a third group of people that have this middle, let's say, annual income with
Right.
an average middle spending score, and points are nicely together. Is it correct?
Yes, yes.
Then we have a fourth group, the green one, with high annual income, but low spending score, which is you see there the group there. Here the points are not very tightly together.
Mm-hmm.
There is a pattern. There is a pattern. So there, in my opinion, in my very humble opinion, there is a pattern, although the points are a little bit scattered. Okay.
Mm-hmm.
Because all the green points are not together. There are some that have high annual income and low spending. And then we go to the last cluster, if I may, to the blue one. Is it correct?
Yes, it's absolutely correct.
Which makes sense from the economic point of view, because the higher the income, the higher the expenditure. Okay. So probably these are different products, the spending of different products according to the annual income. So here in the last cluster, there is a pattern there. You can see that they are clustered, but the points are also scattered. Okay.
Mm-hmm.
So we have three clusters, the blue, the red, and the purple, that are highly tighted, not
Right.
scattered points. Whereas we have two clusters that you see that there is a group there, although the points are a little bit scattered.
Mm-hmm.
I don't know whether you would agree with this analysis.
No, yes, absolutely. And since we
Yes.
have considered only 5 clusters, perhaps
Yeah.
if we had taken 7 or something, maybe these points might end up becoming a different cluster. But the thing is that the green and the blue cluster it's quite far from the other points, right? So
Yeah.
they have formed a separate cluster. But it's true, like this is quite scattered, and perhaps if we had given a higher number of clusters, because we are the ones putting in based on our reasoning. So if we give a higher number, maybe we'll have one more category of high annual income, super high income, and low spending, and another one on the top here, perhaps. Right? But
Or
that's
maybe
all.
not. Or maybe not.
Yeah, or maybe
Maybe
not.
yes, or maybe not.
Right, right.
We should
So,
we should perform the cluster analysis with more clusters to see whether it happens or not. But I think this graph is very nice because we can see it. Okay, the patterns, the expenditure patterns.
mhm.
Probably these are different products according to the annual income. Okay,
Yeah.
so there is no causality, but there's no causality in the sense that we are not analyzing, as we did before, a explanatory variable.
Mhm.
And explained variable in the regression analysis. Here we are analyzing the topology, not
Yes.
their
Just based on.
behavior. Yes. Thank you, Marlene.
Thank you. And I just want to let you know that, I mean, to get these graphs, okay, it's not, I didn't sit and write all these lines of code. You get these kinds of, I mean, there are so many people who have written the code already. You can adjust according to your requirements. So we can, I mean, it's not so difficult to create these visualizations. So just want to like let you know that you can explore on this also, right? You can get these kind of codes, you can make some changes, and you can add one more scatter plot if you have one more cluster, things like that. You can play around with the labeling, and you also see that it's just 1 2 3 4 5. It's just normal labeling, right? And we are the ones who have to like define what this cluster would mean. Like Beatrice said, low income, low spending. So you can label that cluster accordingly, right? the machine will only tell us 1, 2, 3, 4, 5. Yep. So yeah, I think that's all I had for unsupervised learning. And so shall we reconvene after a break, or would you like
Shall
to?
we, Belen?
I think we need to stop for some time, no? Another 10 minutes and we finalize with the last session. Is that okay?
Okay, so
Yeah.
lovely. Thank you so much, Marlene. I'm stopping the recording.
Yeah, thank you so much.